Chapter 6, Structural Analysis. All right, class, today we are going to learn how engineers figure out if something like a bridge or roof truss is strong enough to hold weight without falling apart. Think about a playground climbing frame made of metal bars. Every bar has to work together to hold the kids up safely. In engineering, we call these bars members, and when they are joined together in triangles, it's called a truss. Triangles are very strong shapes, so engineers love to use them to build bridges and roofs. Let's imagine a roof truss. When it rains or when snow piles up on the roof, the weight pushes down on the truss. That push travels through the truss to the walls. Engineers need to figure out how hard each bar in the truss is being pushed or pulled so we can be sure none of them will break. Some bars get stretched out. That's called tension, just like when you pull a rubber band. Some bars get squished. That's called compression, like when you press a sponge. Now, how do we figure out which bar feels what? First, we assume that all the weight is pushing only at the joints where the bars meet. This makes it easier to calculate. Then, we also imagine that the connections are like smooth pins, meaning the bars can rotate freely and don't resist turning. There are two simple ways to solve these puzzles. The first is called the method of joints. Here, we zoom in on one joint at a time and draw arrows showing the direction of all forces. If a bar pulls away from the joint, it is in tension. If it pushes into the joint, it is in compression. For each joint, we make sure the arrows pointing left and right add up to 0, and the arrows pointing up and down also add up to 0. This way, everything balances just like a seesaw. The second way is called the method of sections. Here, we imagine cutting the truss into two parts and looking at one side. Then we use our balancing tricks on this smaller part. We can use three equations: forces left-right, forces up-down, and spinning around a point called moment. This method is great when you only need to know the force in just a few bars without solving the whole truss. Before starting, engineers often check for zero force members. These are bars that don't have to carry any force at all for certain loads, but they help keep the truss stable, like a seatbelt that's not being used but is ready just in case. Sometimes trusses aren't flat but go into 3 dimensions, like a tower of pipes. Then we call it a space truss. We have to use 3 force directions: left, right, up, and down, and sometimes even think about how it might twist. Lastly, we have frames and machines. Frames are like tables or playground swings that hold weight without moving. Machines are like bicycles or cranes where parts move. When we solve these, we break everything into parts and draw free body diagrams just like we did for joints. Each part has to balance in every direction and every spin, so nothing moves unless we want it to. In summary, structural analysis is like solving a puzzle. We make sure every piece works together, every push and pull is balanced, and every spin is stopped when needed. This way, engineers can design safe bridges, buildings, and machines that don't fall down, no matter how big or complicated they are.